Okay, so the recording is started. So if you, at this point, you can please type your name into the chat. That way we'll have your record for attendance and we'll make sure that everybody gets the data that they need. Okay, one more minute. Okay. One second. Okay, good. Okay, good. All right. So welcome everybody. Thank you. Thank you for coming. Looking forward to having class today. A couple of announcements. Next week is the last class of the semester. There's going to be a little break before we resume in the spring, and I think there may be a time change if people want it. I'm going to send out a survey to see if people like this time, or if they'd rather meet on Friday, or if they would rather shift the time a little. I'm pretty flexible, so I'll send out a survey and people can say what they'd like. Okay, let me everybody. Okay, so I'll send that out, but next week we'll be at the same time and we'll be the last meeting of the semester. Okay, so I got a couple of homework solutions, so I was very happy about that. Everybody who sent me homework problem solutions was correct. And this week's homework was probably not as hard as some of the other ones, but it's good to get some practice with exercises. I think the homework that I'm assigning this coming week will be a little bit more difficult and maybe a little bit more interesting also. So we'll see that at the end of the class today. Okay, so what have we been talking about? So we've been talking about probability. We're basically finishing up our probability unit today. And so I want to, and in particular, we're talking about discrete probability. So I want to talk about what is the general principle of discrete probability that we've been using. So this is a review. So if we suppose that there's n equally likely possibilities for how an event can happen, and that m of these possibilities we're going to call successes, then the probability of success is m over n. Okay, good day, Linford. Good to see you. Um, and what is the notation that we use? That if A is an event, then we write P of A for the probability of success. So the P here stands for probability, and this number is always between 0 and 1. If the event is impossible for it to happen, then it will have probability 0, and if the event is certain to happen, then it will have probability 1. Okay? So, great. So that's our notation for probability. And a basic example of this is that if you roll a standard die that has 6 sides, then the probability of getting a 2 or a 5 is 2 out of 6 because there's 6 possibilities, but only 2 of them are successes, getting a 2 or a 5. So that's 2 out of 6. And as a fraction, you can reduce that to 1 out of 3. Okay. So this was the basic idea of probability that we talked about last week. And I wanted to recall the law that basically everything is going to follow from is this one law. So this theorem, which is the law of independent probability, which says that if A and B are two independent events, so this is very important. Oh, yes, question? Moscow? Question? No. Okay. Okay. So what does it mean that you have two independent events? That means that the probability of whether B succeeds is not affected by whether or not A succeeds. And so then this law of independent probability says that the probability that A and B both happen in this case is P of A times P of B. And we mentioned this last time, but it's worth repeating again, is that this is the probability analog to the multiplicative principle in combinatorics. Okay, that if you're making two independent choices, the total number of ways of making it is the number of choices for one times the number of choices for the other. Okay? So this is the law of independent probability, and it's probably the most important law that we use. We use it more than anything else. And there's one other thing that I wanted to recall before we go over the homework is
C'est vrai?
condition. Sorry, question? Yeah, Amasko? Okay, Amasko, if please keep muted
Mais
unless you have a question. Yep. Okay. Um, Okay, so conditional probability. This is also a review from last time. So often we're in a situation where we have two events X and Y that are not independent. We're going to see a lot of that today, non-independent events. And in that case, we often want to determine the probability that X happens given that we know that Y has happened. Okay? And the notation that we use for this is we say P of X given Y. So we say that probability of X given Y. Okay, that's how we say this. Okay. Um, so the probability of X given Y. And then we have a theorem, which is the more general law of multiplicative probability, not necessarily independent. Oh, I missed a B here. Probability, which is that suppose A and B are two events, we're not going to assume that they're independent, then the probability of A and B both succeeding is still the probability of A, but now instead of just multiplying it by the probability of B, we have to multiply it by the probability of B given A, right? B given A is the probability of B succeeding given that A succeeds. And what's the intuition here? For A and B both to succeed, well, we need A to succeed. And I'll say, now that A has succeeded, we need B to succeed, right? So, and then the probability, so the probability of both is the probability of A. And now for calculating the probability of B, we can assume that A has already succeeded. So that's why we have the probability of B given A as the next term. Okay. So we need one to succeed, and then what's the probability that the other has succeeded? We don't care about calculating it if A fails. We only care about calculating it if A has succeeded. Because if A fails, then they can't both succeed anyway. So you need A to succeed, and then to calculate the probability of B, you do it conditional on A. You do it given A's success. Okay? So this is the law of multiplicative probability. And so we're going to see in one of the homework questions, or maybe in two of the homework questions, how this figured it. Okay, before we move on to review the homework, any questions on the law here? Okay, great. Okay, so let's go over the homework. This should be pretty fast because I think the homework was not terribly difficult this week. So, first problem, a blue urn contains four black marbles and two blue marbles. A black urn contains four black marbles and 11 blue marbles. One marble is taken at random from each urn. What is the probability that both marbles are blue? So sometimes it's good to just give yourself events. So let A be the first marble is blue. Oh, sorry. And we let B, the event be the second marble is blue. So the question is, are A and B independent events or not? So are A and B independent from each other?
They are independent.
They are, right. Why are they independent? So, James, can you explain why they're independent?
Yes,
Yep, or yes?
they
Enoch,
are
yeah?
independent because we are.
Or whoever's explaining, yes. Anybody can explain why they're independent.
Hello?
Hello, yes.
They are independent because we are two different forces there.
Exactly. Right? You got two different boxes, and you're picking one from each box. So whatever you pick from the first box does not affect what you pick from the second box, right? You don't have any dependency. So these are independent, and so this means that you can use the law of independent probability. Right? We
Hello,
can use the yes, Princeton.
yeah.
Did you have a
I think we
question?
have. Yeah, I think we have to add on the marble, and then we get the total. Then we'll be able to get the blue marble.
hmm
That is blue. Yes.
Yeah,
So add total, which will give you the 21.
exactly. So to set that up, what we want to do is we want to do the probability of P of A and B by the law of independent probability. That's P of A times P of B. And now, Princeton, I think what you're mentioning is how do you figure out P of A and how do you figure out P of B? And to do that, we need to know the total number of marbles. So what's the probability that we pick a blue marble from the first urn?
It will be 2/6.
Right, exactly. So it's 2 over, 2 plus 4, which is 2 over 6. And then probability of a blue marble from the second urn is
It will be 11/15.
great, exactly. 11 over 4 plus 11, which is 11 over 15. So this reduces to 1/3 times 11 over 15, which reduces to 11 over 45. Okay, so this is very straightforward problem in independent probability. Okay, you have to establish that the events are independent, and then you just multiply the probabilities together. So in this case, that works pretty easy. Okay. Okay. Any questions on this? Okay, should be pretty straightforward. Okay, let's look at number 2. So now here, a box contains 3 red balls and a green ball. And now we say if 2 balls are chosen from the box, what is the probability that the first one is red and the second is green? So I want to set this up the same way that we set up the previous problem. So I'm going to give names to the events. This is always a good thing to do. So again, I'll call them A and B. So I'm going to say I'm going to let A be first ball is red. And then I'm going to let B be the second ball is green. Okay. And so now the question is, are these events independent? Is it independent for the first ball to be red and then for the second ball to be green? Is the probability that the second ball is green, does that depend on whether or not the first ball is red?
The
Well,
question, please.
Yes. Yes. Sorry, I have you as Techno Spark. I don't have your name.
Oh, Armstrong. Oh,
Oh,
wow.
hi, Armstrong. Yeah.
Yeah. The question,
Yep. So are they independent or dependent?
I'll say independent because there are two favorite icons.
Hmm.
We have
Okay.
red in a symbol. We have red. We also have green.
Right. So
So
remember
that's
what is, sorry, yeah, keep going.
I said there are two favorite icons.
Okay. So that's true. They're definitely two separate outcomes. The first ball is red is separate from the second ball is green. But let's go back and remember what's the definition of independent in probability. So we go back. Independent means what? It means that the probability of B is not affected, underline that not, is not affected by whether or not A happens. So let's translate that to our case right now. So we're saying the probability that the second ball is green is not affected by whether or not the first ball is red. So let's think about that. Well, if the first ball is red, the second ball
It
might
will
be
be
green.
affected.
Yeah,
It's not about be affected. I believe so.
it's going to be affected, right? Because if the first ball is green, the
Yeah.
box only has one green ball. So if the first ball is green, there's no way the second ball is going to be green, right? Because the green ball was already chosen first. So that means that depending on how the first choice is done, whether A succeeds or not does affect the probability of whether B succeeds. So we have to say here is that these events are not independent. Okay, these events are not independent. Okay. So these events are not independent, right? Okay, so these events are not independent. Um, great. So these events are not independent. Um, so it means we can't use the law of independent probability. So we have to use instead the law of multiplicative probability. So we have to use the law of multiplicative probability, right? So we have to say the probability of A and B is equal to the probability of A times the probability of B given A. Okay. So what is that? We have to figure out what that is. So what's the probability of A? The probability of A is that the first ball is red. So there's three red balls and one green ball. So the probability that the first ball is red is
3 or 4.
3 over 4, exactly. Now we need to know what the probability is of B given A. So, we have red, 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 and green. And now, so the first ball is red. So if we choose the first ball red, I'm going to cross out the red. And what we're left with now is two red balls and a green ball. So what's going to be the probability of, so what's now going to be the probability of the second ball being green?
1
One
over
over three.
3.
1 over 3, exactly. Okay, and so this comes out to be 1 over 4. And we should notice that this is different from the result we would have gotten if we had tried to use the law of independent probability. If we tried to use independent probability, then we would say, well, the first ball being red, that probability is 3 out of 4. Second ball being green, that probability is 1 out of 4, right? There's 4 balls. And we would have multiplied them together and gotten 3 out of 16. And that would be the wrong answer. So you have to use the law of multiplicative probability when events are not independent. Okay, in this case, we get 1 out of 4 is the actual answer.
Yeah. So that's a double.
Yep.
Hello then. Hello,
Yep.
Mr. So the
Hello,
total
sir.
probability of this ball,
Hmm.
this football is full, right?
Yep.
But looking at it, this one is saying that a boss contains 3 red balls and a green ball.
Hmm.
And then coming to the other side, say if 2 balls are chosen from the boss, what is the probability that the first one is also red? So this is now also part of the 3 red. Oh, okay, I understand. We're already mentioned 3 red, yeah, actually.
Okay. So is it okay?
Yeah, it's okay
Okay.
for me.
Great.
Yeah, okay, yeah,
Other
done.
questions?
Hello,
Yeah.
sir.
Yeah, Prince.
Yeah, Prince. Yeah, I have a concern here with what makes this question to be dependent probability? Is that because all two are coming from the same angle that will make it to be dependent probability?
Yeah, exactly. That's why this is different from the first question. Because look at these 4 balls, right? If we choose a red one, then the chance of getting a green is 1 in 3. But if the first choice is a green one, then the chance of getting another green one is 0, right? So, and that's different. So what it says is that whether or not the first one is red, whether or not the first event succeeds, that has a real effect on what is the probability of the second event succeeding, right? If the first ball succeeds, if it's red, then the second event can succeed. You can get a green. But if the first ball that you choose is green, meaning the first event fails, then there's absolutely no chance of the second event succeeding. Okay?
Okay,
So the way you
okay.
make that
Then
first choice is going to affect the probability for the second choice. That's why these are not independent.
yeah, and based on the question what you gave, you said the proper what is the probability that the first one is red, and then in the second thing again, you say, and the second is green. So I'm looking at it to be seeing balls to take one red
Hmm.
and one green. That's how I'm looking at it. So
Yeah,
to
but it
to
has to be
say
the first one red and
two,
then the second one green, not the other way around.
okay,
So in this case, priest, I think that
yeah,
if you put your hand in this box to pick another after you have picked the green, there will be no
Hmm.
green in this box now.
Yep.
Yep, so there will be no green because we only have one green in this box. And the second chance of winning the green, it will
Hmm.
be like 0.
Hmm. Yeah, so the second would be 0, right? So if the first one was green, then the chance of the second one is green is 0, right? So
Yeah,
that,
Robert.
yes, that makes a difference. Yeah,
okay,
Abraham?
it's also
Yeah, just to add up, that is oscillation without replacement.
Yes. That was assumed here. I should have said this. Yeah, so I should have said this more clearly. So I want to say without
Replacement.
replacement. Sorry, I should have been clearer about this. Yeah. Yes, if they were chosen with replacement, then they would be independent. Yeah. So I apologize for that.
yeah. So it's honestly so it means there's no replacement for any
Yeah.
people. Yeah,
You don't put the ball back in.
yeah.
Yeah.
You don't put it back.
Yeah.
Okay, it's honestly.
Okay. Good. Okay.
So
Okay. Any
Emmanuel,
uh any
your
any any
Bible.
other questions on this?
Hello, sir.
Okay, yes. Other questions?
Hello, sir.
Yeah, Rush.
Yeah, the 3 or 4, I don't know how much you got that.
Oh, the 3/4 is just because the box has 4 balls, and A is the event that the first ball is red. So 3 of the balls are red out of a total of 4. So the chance of getting a red ball is 3 out of 4. Because it's total 4 balls,
First
3
only
reds and
4.
1 green.
Oh,
Yeah,
God.
let me try to understand there.
I
Mhm.
understand.
Yeah,
I understand.
yeah.
Okay.
We say we have. If me ask the question, we have a 3 red and
I
3 red
understand it,
balls
Chief.
and a green ball. So a green mean one. So the green boy is 1 plus the 3 red is what gives the denominator to
Yeah,
be
okay.
4.
I think Rash understands. So we're good. Any other questions on this one? Okay. All right, great. Okay, let's move on. Okay, so exercise 3, this is going to be a different type of exercise. This is going to be more a combinatorics one. So suppose 2 dice are rolled. What is the probability that the sum of the 2 numbers is odd? So, first die has 6 possible outcomes, 1, 2, 3, 4, 5, 6. And then the second die also has 6 possible outcomes, 1, 2, 3, 4, 5, 6. Okay. Okay. So, okay, so the first die is 1, 2, 3, 4, 5, 6. Second die is 1, 2, 3, 4, 5, 6. Okay, so we want to know what is the probability that the sum is odd. So we could just go ahead and, just try, write down all of the possibilities, right? So in this case, we actually have 36 total outcomes, right, with the first die and the second die. But and we want to know how many of those are odd. So we want maybe a creative way of counting rather than literally just going through all 36 outcomes and figuring out which ones have an odd sum. Maybe there's a clever way that we can add this up and figure it out. So does anybody know a clever way to count the total number of outcomes that are odd?
Okay.
Yep.
You see, man, you just asked.
So I want to know
Yeah.
how can we count the total number of odd outcomes?
Yes. The first thing we know that on the dark, the first that we have 6 outcomes. The second that we have 6 outcomes. So to arrange it, we need a space. We need a little space. Yeah. So we need a little space to get it 36 total. So the first thing you can start with 1. Yeah, you can start with 1 command 1, 1 command 2.
Yeah.
Yeah. We need a
So
space.
we can
Yeah. So
write
you
them
need to
all
get 1
down if we
command
want,
1.
right? Yeah.
Yeah, 1 command
Yeah.
1, 1 command 2, 1 command 3, 1 command 4, 1 command 5, 1 command 6. Then you can with 2 command 1.
Yeah. So, right. So this is one way
Yeah,
we
then
can
you
do it,
start with
right?
2 command 1, 2 command 2, 2 command 3.
Right. So this is one way. Okay. So I'll write the whole thing
Yeah,
down just because it's not that bad, right?
hello?
Yes.
So we have another way here.
Well, let me actually just do it this way. We'll have room for both ways.
Hello?
Hello. Yes.
Hello?
Give me 1 second. So right. So one way of doing this is to just write down all the ways, right? And this takes a little bit of time, but it's not so bad. So 5, 2, 5, 3, 5, 4, 5, 5, 5,
5,
6,
6,
6, 1.
6, 1, 6, 6, 3, 6, 4, 6, 5, 6, 6.
Okay. So you can do this, and I'm not going to necessarily spend so much time on this, but if you want to look at which ones are odd, you can just start circling, and if you count them all, I'm just circling all of the ones where the sum is odd. And if you circle all these ones where the sum is odd and you count them up, it turns out that you get 18. Okay, so this turns out to be 18 total. Okay, so you get 18 out of 36 if you count this. But what would be maybe a faster way to see this without actually writing down all the possibilities? Is there a faster way to just count all of the ways to make something odd?
Yes.
Yes.
Let me try.
Yes. Yes. Enoch?
Yeah. Hello?
Yep. Yeah, Enoch. Or sorry. Yeah, Enoch.
Hello?
Yeah, hello.
Yes. It's
Or
Armstrong.
Armstrong. Yes, Armstrong. Yep.
Yes. Okay. We know very well that to get an odd number, we need to get one or one even.
Right.
On the first die, there we get 3
odd number, then
Right.
then we get 3 even number.
Yeah.
So that we get multiply 3 by 3, we
Right.
get 9.
Exactly.
The same thing with the second die.
Right.
Yeah, 3 times 3 we get 9.
Exactly. Perfect. Yeah. So this is much
So
faster.
we have now what 36 plus now what 36.
Mm-hmm.
We should get 18 what 36.
Yeah. And I'll actually just write that as 9 plus 9 over 36, which is 18 over 36 equals 1/2. Right. Perfect. Yeah. So this way is a little bit faster because we know that to get an odd sum, you need one to be odd and the other one to be even. So if the first is odd and the second is even, there's 3 times 3 ways of getting that to happen. That's 9. And if the first is even and the second is odd, then there's 3 times 3 ways of getting that to happen, which is also 9. Okay. Um, so that is it, right? Okay. So that is it. Okay, so we get 18 total successes and 36 total possibilities. So the probability is 18 over 36, which is 1/2. Okay, any questions on this?
Yes, that are over.
Yes, Princeton.
Yeah, that. I have a question that.
Well, I think Princeton was first, and
Prince.
then you can ask. No, but Princeton had asked
Yeah.
first, I thought.
Okay.
Or not. I mean, Prince, you can
Okay,
ask the
yeah.
question also.
I'm a little bit confused.
Mhm.
How we got the 3 times 3?
Yep.
Yeah, actually, how we got the 3 times 3 together? I honestly, I got the 36. Even
Mhm.
because of 2 darks, we can even say 6 times 6, we will get
Mhm.
36. Yeah. But now, my question is, I'm confused how we got the 3 times 3 together 9 and all to both sides.
Right. So we're looking at how many ways can the first die be odd and the second die be even. So these are independent things because it's 2 different dice. So what are the possibilities for the first die to be odd? The possibilities are 1, 3, or 5. So that's 3 possibilities. So we get a 3 over here. And for the second die to be even, we have 2, 4, or 6. That's also 3 possibilities. So we have a 3 here. And because we're counting independent events, we multiply them. So the total number of ways of getting the first one to be odd and the second one to be even is 3 times 3, which is going to be 9.
It's honestly that
Okay,
I got everything now.
great. Okay, other questions?
Got it. I got it clearly now. Thank you. I got it.
Okay. Good. Does anyone else have a question, or should we move on? Okay, so let's move on. Okay. So today we're going to be talking a lot about conditional probability, which is where a lot of the applications of probability come in, and we'll see an interesting application at the end of the day. So, what's another way of thinking about conditional probability? So, another way of thinking about it is that if X and Y are 2 events, then the probability of X given Y, you can think of it as the probability of X and Y divided by the probability of Y, right? This is just another way of restating the law of multiplicative probability, right? If we let me just make this red for a second. Right? This is equivalent to saying that probability of X and Y is equal to probability of Y times probability of X given Y, which is the law of multiplicative probability. Okay, so this is the law of multiplicative probability over here. But it's just a different way of thinking about it. If you want the conditional probability, so what's the probability of X given that Y happens? It's the probability that both X and Y happen divided by the probability that Y happens. Okay, so it's just a rearrangement of the law of multiplicative probability. So let's use this to show that if X and Y are independent events, then the probability of X given Y is the probability of X. right? I mean, that's good, right? Because if x and y are independent, then the probability of x should not be affected by whether or not y appears, right? Shouldn't be affected by whether or not y appears. So let's look at that. So if x and y are independent, then we know that by the law of independent probability, probability of x and y is equal to the probability of x times the probability of y. Right? This is independent probability. This is the law of independent probability. So probability of x and y is equal to the probability of x times the probability of y. And so now let's show what we want to show. We want to show that the probability of x given y is equal to the probability of x. Well, we have that the probability of x given y is, well, we have this event over here. We saw that this is equal to the probability of x and y divided by the probability of y, right? This is just by the first bullet point over here. X and y divided by probability of y. Well, that's equal to the probability of x times the probability of y divided by the probability of y. And now we can cancel out probability of y, and what we're left with is exactly probability of x. Okay? So this shows us exactly what we would expect to be true, which is that if x and y are independent, then whether or not y happens shouldn't affect the probability of x at all. So that means the probability of x given y is just the same thing as the probability of x, because x doesn't see y. It doesn't care about what happens to y, right? So conditioning it on y, saying given y, just won't affect anything. Okay, so probability of x given y over here is just the same thing as the probability of x. Okay, any questions on this?
Hello.
Okay. All right. Any questions? Emmanuel, I'm not getting you clearly. You have to mute. I'm not really getting you. No.
Hello.
Hi, I hear that you're talking, but it's not coming through clearly. I can't understand.
Hello.
Hello? Yep.
Now you're talking.
Yep. Okay. Okay. Let's move on. Okay, so there's two more laws for today. So this one is called the law of total probability. So this states that if an event X depends on an event Y, and Y has n possible outcomes, Y1 up through Yn, then the probability of X is the probability that Y1 happens times the probability of X given Y1 plus the probability that Y2 happens times the probability of X given Y2 plus and so on up through the probability that Yn happens times the probability of X given Yn. I'll say the idea of this, but I think it's going to be more clear when we do an example. So the idea is that one of y1, y2 up through yn has to happen. So what is the probability of x? It's equal to the probability of x and y1 plus the probability of x and y2 plus and so on plus the probability of x and yn. Right? Because one of the yns is going to have to happen, right? So something y1 through yn is all going to have to happen. So the probability that x happens is the same that x happens and one of these things happens. So x and y1 or x and y2 or x and yn, one of these things has to happen. And now you use this multiplicative probability. So now I'll say here, multiplicative probability. This probability of x and y1 is exactly equal to the probability of y1 times the probability of x given y1 plus the probability of y2 times the probability of x given y2, and then so on, plus the probability of yn, probability of x given yn. Okay. Okay, so this is the derivation of the law, if you want. So you have y can have all sorts of different outcomes. They might all affect the probability that x happens. And the total probability of x happening is you have to go through all of the outcomes of y and figure out how they're going to affect the probability of x happening. Okay. So this really does just follow from the law of multiplicative probability. So maybe before taking a question on this, let's show this in an example, which actually I think once you see it with an example, it's going to be pretty clear. Okay, so what's an example? So suppose politician A and politician B are running against each other for office. So if A is elected, there's a 60% chance that taxes will be raised. If B is elected, there's a 70% chance taxes will be raised. Current polling suggests that A has a 35% chance of being elected. So what is the probability that taxes will ultimately be raised? So to do this, we're going to use the law of total probability. So I'm going to let x be the chance that taxes are raised. Right? That's what we ultimately want to figure out, is what's the probability that taxes will be raised, right? So if we're going to use the law of total probability, this is what we're going to try to figure out, is this P of x. So now the other event is who gets elected. And that, in this example, has two possible outcomes. Politician A can get elected and politician B can get elected. So I'm going to say, so the event y1 is going to be the event that A gets elected. And y2 is going to be the event that B gets elected. Okay? So then the law of total probability what does it say? It says that the probability of x is equal to the probability of x given y1 times the, well, let me write it so that I'm consistent with how it was before. So it's the probability of y1 times the probability of x given y1 plus the probability of y2 times the probability of x given y2. Okay? Okay, so James has an answer, which could be right. I don't know. I haven't done the problem yet, but let's try to work it out. So, okay, so now we have to work out what these probabilities are. So what's the probability of y1? That's that A gets elected. We've seen 35% chance there. So this is 0.35. Now, what is x given y1? That says that what is the chance that taxes are raised given that A gets elected? So if A is elected, it says there's a 60% chance that taxes are raised. So this is going to be exactly 0.60. Okay. Similarly, what's the chance of y2? What's the chance that B gets elected? Well, if A has a 35% chance, then B has a 65% chance of getting elected, right? B is the other candidate. So we've got 0.65. And now what's the probability of taxes being raised if B gets elected? Well, we're saying 70%. So times 0.70. Okay, so this is what the law of total probability tells us. And so this is going to be 0.21. And this is going to be 0.455. So James is right. So this is exactly going to be 0.665, or if you want to do it in terms of percentages, 66.5%. So about 2/3. Okay, so this is the law of total probability in action. Okay, we have two different possibilities of something that can happen. Either A can get elected or B can get elected. We have to figure out both of those probabilities and then multiply them by the probability that the thing that we're trying to calculate, in this case, taxes getting raised, multiply them by the probability that taxes get raised, assuming one of these two things happens. Okay, so when we punch everything into the law of total probability, this is what we get. We get 66.5%. Okay. All right. Any questions on this? Okay. No questions on this? Okay, so it's a pretty straightforward application of law of total probability. Let me give you a graphical way to do this, which is maybe a little bit easier to understand. So I'm just going to show the same problem but graphically. So same problem graphically. Well, what we do is we have two choices, right? So first, I'm going to start over here. I'm going to draw a little tree diagram. So this is like the tree method. Tree method. So over here we have A getting elected, and over here we have B getting elected. In the problem, this was 35% chance, and B getting elected was a 65% chance. And now we have taxes raised, and over here we have taxes raised. And the probability that taxes were going to be raised over here was 0.60, and here is 0.70. And then what we do, yeah, so the final probability is exactly right. It's this 0.665%. It's exactly what you wrote. Yeah, 66.5%. And so now the way we calculate is we multiply through all of the branches of the tree. So I'll just say multiply through each branch of the tree through, and then add the different branches. So this is exactly the same computation we just did. It's going to be 0.35 times 0.60 plus 0.65 times 0.70, and that turns out to be 0.665. Okay, so we can think of it as we have these two branches of the tree, and we're going to multiply through each branch, and then we add them together. So, I mean, this is just the law of total probability. There's not anything new going on here, but sometimes seeing it visually makes it a little bit easier to makes it a little bit easier to learn or to retain. Okay, so I want to show this method also. All right, any questions on this? Okay, great. Okay, good. Okay, so let's do another example here. So it's conditional probability and what I'm going to call reverse conditional probability. So let's say that a bag A has 5 white marbles and 2 black marbles, and a bag B has 3 white marbles and 5 black marbles. A bag is chosen at random, and a random marble is taken from the bag. And now I'm going to tell you that the marble is white. So the question is, what is the probability that the bag chosen was bag A? So this question is a little bit harder than if I asked it the other way, right? If I said we choose bag A, what's the probability that the marble is white? Then we would just say, okay, well, bag A has 5 white marbles and 2 black marbles, right? So 5 white marbles and 2 black marbles just means that the chance is 5 out of 7. But that's not what the question is saying. The question is saying, I'm choosing a random bag and I'm choosing a random marble, and then I come up with a white marble, or somebody chose a random bag and chose a random marble, and then they came up with a white marble. And the question is, how can we deduce whether or not it was likely that they chose bag A to begin with? So it's a little bit more of a subtle question. Okay, and I find that the best way to answer this kind of question is to use what I call the box method. Okay, so for this question, there's really two different things. So I draw a box like this. I draw a 4-square box. So here I have bag A and bag B, and over here I have white marbles and black marbles. Okay? And so what I'm going to do is I'm going to fill in each box with the probability that the corresponding events both happen. So this box is going to be the probability that I choose bag A and a white marble. This is going to be bag B and a white marble. This is bag A and a black marble, and this is bag B and a black marble. So let's see what we have here. So A and white, well, the bag is chosen at random. So there's always a 1 in 2 chance of choosing bag A. And then if I choose bag A, then the chance of getting a white marble is 5 out of 7. Right? Because the chance that I do A and white is the chance of choosing bag A, and then the chance of choosing a white marble given bag A, which is 5 out of 7, because there's 5 white marbles out of 7 total marbles. Similarly, for bag B, I have 1 out of 2. B has 3 white marbles and 5 black marbles, so the probability of choosing a white marble from bag B is 3 out of 8. Now, what do we have for A and black? Well, A has a 1 in 2 chance of being chosen, and then the probability of getting a black marble is 2 out of 7. And lastly, B has a 1 in 2 chance of being chosen, and the probability of getting a black marble from B, well, it's 5 black marbles out of 8 total. So 1/2 times 5 over 8. So I fill in each of these boxes with the probabilities. So now we say that the marble is white. So what is the probability that the bag chosen was bag A? So if the marble is white, what that means is that I'm really only focusing on the top row of this box, right? So I fill in everything in the box, but really all that I need is the top row, because we know that the marble is white. And so what do we have? Well, we're going to use the law of multiplicative probability. And that's going to say that the probability that we have white given A, or it's really like maybe instead of saying use the law of multiplicative probability, I'm going to say we're going to use our interpretation of conditional probability, this is what we saw on an earlier slide. So the probability that we have a white marble, the probability, what do we want to know? The question is asking for what's the probability that bag A is chosen given that we have a white marble? Well, this should be the probability that we have bag A and a white marble divided by the probability of having a white marble. Right? This is exactly this equation, that the probability of having something given something else is the probability that they're both true divided by the probability that the condition is true. Okay, so the probability of A given white is the probability of having A and white divided by the total probability of having something white. And now with our box, we can just fill this all in. What's the probability of A and white? Well, we see that. It's just 1/2 times 5/7, right? So this is equal to 1/2 times 5/7. And now what's the probability of choosing white? Well, the probability of choosing white is just the probability of white and A plus the probability of white and B, right? Both of these outcomes are a white bag. So down here we have 1/2 times 5/7 plus 1/2 times 3/8. Okay. So this becomes 5/14 divided by 5/14 plus 3/16. And I'm just going to do this on the calculator rather than filling this all out. Let me just do this on the calculator. So 5 divided by 14 divided by 5 divided by 14 plus 3 divided by 16. And that comes out to be, also 0.655. Also, this becomes roughly 0.656. Okay. I'm sure we can calculate it exactly if we want to. Yeah, so this is saying that actually this gives us 40 over 61. There's no way that's right. Okay, well, you can figure out what it is as a fraction. I don't really feel like doing it now. Okay, 40 out of 61. That seems right enough. So 14 and 16. Yeah, so the common denominator here, well, if you multiply by 112, then you're going to get, so 14 and 16 have 112 as a common denominator, right? That's 14 times 7. So, no, 14 times 8, right? So you get 40 out of 35 plus 21 is 40 to 50, 40 out of 56, or
Well,
it becomes 40 out of 61 out of 21, and then 5 times 8. Yes. Okay, so this becomes 40 out of 61 if you want to do it exactly. Okay, so you can do that as an exercise if you want. Okay, question? Yeah, Enoch? No. Okay, so this is what I call the box method. And there's really no way to just look at this and say the answer. You have to go through some sort of method because the question that it's asking, again, is pretty subtle. It's saying you observe something, that the marble is white, and then it wants you to figure out the probability of something unobserved, something that you don't see. Like, was the bag A or bag B? You can imagine your friend is doing this behind a door. They pick a bag at random, and then they pick a marble, and they show you a white marble. And you're trying to deduce the probability of something that you can't see. So that's why these are a little bit more complicated than the other problems, okay? If you want to know what's the probability of A, given that the bag is white, you need to do this kind of box calculation using this interpretation of conditional probability. Okay. Questions on this example? Okay. So let's look at another one, which is maybe a little bit more practical. So let's say that you have a disease that the prevalence in the population is 1%. Okay? So we design a test for the disease that gives the correct answer. So it says, yes, you have it, or no, you don't have it. It gives the correct answer 95% of the time. Okay, so it's a pretty accurate test. So the question is, suppose I take this test and I test positive. Now, what is the chance that I actually have the disease? Okay. And this doesn't necessarily look exactly like the other question, but it's just going to be the same thing. It's going to be this box method. We use this box method, then we have two variables, right? What I should really say is this is used when figuring out the probability of something unobserved from something observed. Okay, we observe the result of the test. We don't observe the disease itself. We need to figure out its probability based on what we did observe, which is the test. But we can do this box method just like before. So we have a box. So here we are. We can test positive or we can test negative. And then we can have the disease or we don't have the disease. Okay? And so we need to figure out what is the probability of each of these things. So what's the probability that we have the disease and we test positive? Well, having the disease, we've got a 1% chance, right? So that's 0.01 times, if we have the disease, what's the chance that we test positive? Well, the disease gives the right answer 95% of the time, right? So if we have the disease, the chance that we get a positive test is 0.95. It's going to be 95% of the time, right? So similarly, what's the chance that we have the disease and test negative? Well, having the disease is again 1% chance. The test is accurate 95% of the time, which means it's wrong 5% of the time. So a negative test is wrong, right? So the chance that we get a negative test here is 0.05. Okay, that's being wrong. Now, what about not having the disease and testing positive? Well, only 1% has the disease. So the chance that we don't have the disease is 99%. So 0.99. And then if we don't have the disease, but we test positive anyway, that's a false positive. Well, the test is accurate 95% of the time. So the chance that it would give us a false positive when we don't have the disease is just 5%. Right? So just 0.99 times 0.05. And now the chance that we don't have the disease is 99, and then that we get a negative result, that's the correct result when we don't have the disease. The test is 95% accurate, so we get 0.95 over here. Okay, so this is our box that we're drawing. All right. We haven't answered the question yet. We're going to calculate the probability, but before I calculate the probability, are there any questions about how we filled in this box? Okay. All right, so now let's actually calculate the probability. Okay, so the probability is, so what are we trying to do? We're trying to calculate a conditional probability. It's the probability of having the disease given a positive test, right? That's the way this question is phrased. It's really a word problem. So what's the chance that I have the disease given that I test positive, right? We observe, in this case, this is always what is observed, and this is what's unobserved. Okay, well, again, we use our interpretation. This is probability of having disease and positive test divided by the probability of just having a positive test. Okay. Okay, so having disease and positive test, that's right up here. This is equal to 0.01 times 0.95 divided by, well, what's the total chance of a positive test? Again, we're only looking at this side of the square. Excuse me.
It'll be 0.05.
So it's 0.01 times 0.95 plus, well, we have to add the other box also, right? So 0.99 times 0.05, right? The probability of a positive test is the entire left side of the square, whereas having the disease in a positive test is just the upper left corner. Okay. So let's see, what is this actually equal to? This, again, I'm just going to use a calculator. So 0.01 times 0.95 divided by 0.01 times 0.95 plus 0.99 times 0.05. So this ends up being equal to about 16%, 16.1%. Okay. And so this is, we shouldn't just say, okay, the answer is 16.1%, we're done. I want to appreciate that this is a very surprising result, right? You took a test that is 95% accurate, and you tested positive for a disease. So if you're not thinking, you would say, what's the chance you have the disease? Well, it's 95%. And the answer in the case of a rare disease is that that's just completely wrong. Even if you test positive, the chance that you have the disease is still only 16.1% in this case. So even with a positive test, you're more likely than not to have the disease. And the underlying reason for this, the conceptual reason, is that this disease is so rare and this test is 95% accurate. That's pretty good, but frankly, it's not quite good enough. And what that means is that the chance of having this disease, the chance of testing positive from a false positive is bigger than the chance of testing positive from actually having the disease. So the kind of moral here that we get from this box method, this law of total probability, is that when something is very rare, if you want to test for it without a lot of false positives, you need an extremely accurate test. So if this test were accurate 99.9% of the time, then your probability would go way up. Then you'd have like a 90% chance of having the disease. But this test is only accurate 95% of the time, which means you're more likely to just get a false positive, which happens like 5% of the time, than you are to actually have the disease. And what this translates into is that even with a positive test, your chance of having the disease is only 16.1%. So it's pretty low. Okay? So a 95% accurate test it seems very good, but it might not actually be accurate enough. In this case, we see that it's not accurate enough to give you a good idea of whether you have this or not. Okay, so any questions on this problem? I think it's a very nice problem and it's very, counterintuitive. It's something to spend a little bit of time thinking about. All right, any questions? Okay, good. Okay, so no questions on this. I want you to understand, I just want to say this one more time. I've said it already, but to understand not just how to get the right answer, but why this answer is surprising. Okay. Okay, so let me say formally what we've been doing. We've been calling it the box method, but what we've really been doing is what's called Bayes' law. So what Bayes' law says that the probability of x given y is the same thing as the probability of y given x times the probability of x divided by the probability of y. Okay, this is actually very easy to prove. And it's used to estimate an underlying or hidden condition from observations. The proof of Bayes' law is very easy, so I'm just going to give the proof right now. Well, the proof is that the probability of x given y is equal, we know that it's the probability of x and y divided by the probability of y, right? We've seen this. And well, the probability of x and y is the same thing. Now we use the law of multiplicative probability. X and y is the probability of x times the probability of y given x, and then divided by the probability of y, right? So the fact that these two things are equal, this is the law of multiplicative probability. All right, I mean, so this is it. This is the entire proof. Okay, so we just have to use kind of the law of multiplicative probability in one direction and then use it again in the other direction. Okay? So it may not be clear kind of what this thing here has to do with what we've just been doing. So what I want to do is do one of the previous examples, but using Bayes' law instead of the box method. So I like the box method. I think it's pretty clear. I like writing down all of the boxes and calculating the probabilities, and that's fine. But I just want to show that if you like this better because it's a simpler formula instead of having to draw a box and do everything, then I want to show that, this is a valid way to calculate the probabilities also. Okay? So let's actually do one of the previous examples. I think maybe we'll only do one of the examples and say for a previous example. Question? Francis? Sorry. Oh, wait, no. Okay. Okay. So let's do this. Let's do which example? Does anybody have a preference? Do you want to do the disease one or the marbles? Which one should we do? Should we do the disease or the marbles? Okay, let's do the disease. Okay, so law of multiplicative probability. So we're going to do the disease. So let's do the disease example. So for Bayes' law, what we want is a conditional probability. So we want the probability of having disease given positive test. Okay? So what Bayes' law says is that this is equal to, right? I mean, this is what we called x, and this is what we're calling y over here, probability of x given y. So what Bayes' law says is that it's the probability of the reverse condition. This is why we call it reverse conditional probability, that this is equal to the probability of a positive test given that we have the disease times the probability of X divided by the probability of Y times the probability of the disease divided by the probability of a positive test. Okay. And what is this? Well, the probability of a positive test given that you have the disease, well, the test is 95% accurate. So given that you have the disease, the chance that you get a positive test is 0.95. Now you multiply that by the probability of actually having the disease, which we said is 1%. So that's 0.01. And now we have to divide by the overall probability of a positive test. And so what we see that we're doing for Bayes' law is the overall probability of a positive test is exactly, what's the overall probability of a positive test? It's exactly this side of the square with the box method. So the overall probability of a positive test is exactly this 0.01 times 0.95 plus 0.99 times 0.05. This is the probability of a positive test. So I'll write that down. So this is 0.01 times 0.95 plus 0.99 times 0.05. And if you look at this, this is exactly the same computation that we did over here. So the answer is going to be exactly the same. It's going to go to 16.1%. Okay, so same as box method. And it's not just that the answer is the same as the box method, but what you do for this is really basically the same thing that you do for the box method. Okay, so sometimes you'll see Bayes' law over here. It's a nice kind of fancy formal way of writing these conditional probabilities, but in practice, I never memorized this law. In practice, for a problem like this, where you're trying to figure out the probability of something unobserved from something observed, I always just use the box method. I think it's easier to do. You get the right answer, and you don't have to remember, like, oh, is the X in the numerator or is the Y in the numerator? This is hard to remember. I like to just write out the box method and figure it out this way. Okay? So for all of these questions, when you observe something and you want to calculate the probability of something underlying that, something unobserved, I think the box method is the way to go. Okay, questions here?
Yeah, hello.
Yes, Emmanuel.
Hello.
Yes,
Are you there,
Emmanuel.
Andrews? Andrews?
Hmm?
Are you there? Yes.
Yes, I'm
Yeah,
getting you
I'm
now.
having some difficulties, but okay. You talk about unobserved probability.
Yeah,
Can you show a little light on that?
sure. So
Yes.
so what is the application here? And a lot of applications, you want to understand something. Are you sick? Do you have some health condition, let's say? Is something going on in your brain? But this is something that you can't directly observe. All that you can observe is a test, right? So if I want to know if I'm sick, if I have the flu, I can't just literally observe if I have the flu. I can take a flu test and I can
Okay.
observe the results of the test, right? The test is either positive or
No, bring
negative.
it.
So what this is, when we talk
No,
about
bring it
observed
over.
versus unobserved, what we mean is you take something that you can see, like a test is positive or negative, a result that you can see. This marble is white. And then you try to infer from that what is the probability of an underlying condition? What is the probability that I have some disease? That you can't literally observe, right? Maybe you can if you have like a microscope but in general, the test is what you observe. The underlying condition is what you want to learn about based on what you can observe. Okay? So, and in this example, a marble is white, but you haven't observed which bag was chosen. So you observe the white marble, and then you try to infer what is the probability that a certain bag was chosen. Okay? So these types of reverse conditional probability are all about taking an observation, a thing that you can literally see, and trying to infer a probability of something that is related to it, but is not something that you can directly see. Okay? And so I
Okay.
think the example of a
Yeah,
disease
thank you.
test is pretty salient. You can't see the disease, you can see the test. But you don't care about the test. What you want to know about is the disease. So you have to figure out the probability based on what you can see, which is the test. Is that helpful?
Yes.
Okay, good,
Yes, it is helpful. Yes,
good.
yeah, it is helpful.
Okay, great. Okay, so I think we're going to finish up. So this homework looks long, but it's just because the questions have a lot of words in them, not because there's a lot to do. Okay? So first homework exercise. So suppose a bag has 2 blue marbles and 3 red marbles. I draw 2 marbles out of the bag. I should say here without replacement. Okay? So determine the probability that the second one is blue as follows. First, use the law of total probability, where the two cases are that the first marble drawn is red and that the first marble drawn is blue. So either of those things can happen, and then you can figure out the probability that the second marble drawn is blue. So you can do a tree method for this. And the second thing is now, once you've solved the previous part, this is kind of a little bit of a trick. Can you figure out an easier way to obtain this answer? So I won't say anything about B. We'll talk about that next week. So number 2, 3 balls marked 1, 2, and 3 are placed in a bag. 1 ball is drawn, the number is recorded, and then it's placed back in the bag. So this is with replacement. The process is repeated 2 more times for a total of 3 balls. The sum of the 3 numbers drawn is 6. What is the probability that the ball numbered 2 was drawn all 3 times? So maybe just as a little hint here, right? How could you get 6? You could draw the ball numbered 2 all 3 times, or you could draw a 1, a 2, and a 3, right? So this is going to be, you can do this with the box method. Okay, so I'll leave it at this. You can do it with a box method or you can do it with Bayes' law, whichever you want. And then number 3, this is kind of like the disease one. So it's estimated that 50% of all emails are spam. A software program claims it can detect 99% of spam emails, and the probability of a false positive, that is, a normal email that is classified as spam, is 5%. So basically, if the email is spam, the program gets it right 99% of the time. If an email is normal, then the program gets it right 95% of the time. False positive is 5%. So the question is, if an email is detected as spam, what is the probability that it's actually spam? So how many of your good emails is this program actually locking away in the spam folder? Okay, so this number 3 here, this is another box method. So you just have to figure out how to set it up with the box method. Okay. And so next week is going to be the final meeting of the semester. And so we're going to review everything that we've done this semester, and we're going to try to place everything into context in preparation for next semester, where I think the participants are going to take a little bit more active role next semester in terms of coming up with sorry, I need to mute everybody. I'm getting an echo. The participants are going to take a more active role next semester in terms of taking topics that we haven't looked at and trying to figure out how we would present these topics in a workshop for other teachers. So we're going to spend a little bit more time on that next semester. So next week will be a sum up of everything that we've done and trying to extract the main ideas from everything that we've done, and it will prepare us for starting in the winter our next work. So as always, I'm going to post the slides on the chat room, and I'm going to post the video to YouTube. Good. All right. So that's it for today. Any questions?
certificate.
Yes. Is Deborah still here? Deborah's not in the room anymore. So I think you need to ask her about the ceremony. So you have to ask Deborah or Sanjay what's going on with the certificate ceremony. At this point, it's out of my hands. There's been funding that's been appropriated for it, and the certificates are there. And the question is just when is it going to happen? But I'm not involved in planning it. So you have to ask her. Okay, let me stop the recording. Has everybody put their name in? I think everybody has at this point. Last chance to type in your name, and then I'll stop the recording. Okay, let me stop.
Yeah, so that is
Yep.
is our